Dehn twist.
Okay, thank you for the introduction. Thank you for coming. So I start with something basic because I didn't know that Heather was planned to talk about her thesis. So I work on symplectic topology and I play with symplectic manifolds. A symplectic manifold is simply a smooth manifold together with a two-form which is closed and non-degenerate. So we have examples include Euclidean space, cotangent bundle, and etc. And a symplectomorphism is an equivalence relation between symplectic manifolds. So a symplectomorphism is a diffeomorphism intertwining the symplectic structure. So simplest example of symplectomorphisms can be given as follows. So when the symplectic manifolds are the same and compact, then you can integrate along a vector field such that the Lie derivative of the symplectic form along with is 0, just simply by definition. So there is another more interesting kind of symplectomorphism called the Dehn twist. And so given a Lagrangian sphere in a symplectic manifold, which is a sphere, a submanifold, such that the symplectic form vanish on the sphere, then we have a standard neighborhood theorem, and you can define a symplectomorphism support inside the neighborhood. So this is the picture illustrating the effect of the Dehn twist. The purple guy is the Lagrangian sphere, and the green ones show you the effect of the Dehn twist. So I've talked about symplectic manifold and equivalence relation. What's next is, for some symplectic manifolds, you can associate to it an A infinity category, the Fukaya category. So objects are Lagrangian submanifolds, and morphisms are basically the K-vector space generated by the intersection points of the objects. And you can define operations by counting disks which satisfy A infinity equations. And equivalence relation for an A infinity category, one choice is a quasi equivalence. So you can, as mentioned in previous talk, but in next talk, so mu1 is the differential and mu2 descend to composition on the cohomology level. So you can take the cohomological category, and an A infinity functor is a functor satisfying A infinity relations which induce cohomological category equivalence. So basically we have symplectic manifold, symplectomorphism, A infinity category, quasi equivalence. And then Sidel proved that for exact Lagrangian, we have an exact triangle. So here L is the Lagrangian, and tau SL is the Lagrangian after the Dehn twist. And so that derived Fukaya category has a triangulated structure, and this is a triangle which can induce a non-exact sequence on cohomology. And the whole picture, so this is just an exact triangle, but actually the Dehn twist induce a quasi equivalence on the derived Fukaya category, which can be formulated purely algebraically. I denote it as TS, and TS on L is tau S on L, up to quasi isomorphism. So next. So now we can look at another triangulated category. So if we have a smooth projective variety, we can define the bounded derived category of coherent sheaf. And one can define a spherical object by just two equations. So the object tensor with the canonical sheaf is isomorphic to itself, and the X ring is the same as the cohomological ring of the sphere. And purely algebraically, using spherical object, one can define an autoequivalence on the bounded derived category of coherent sheaf. So this is a summary. So symplectic manifold, Lagrangian sphere, Dehn twist, derived Fukaya category, spherical object, spherical twist. And on the third column, bounded derived category of coherent sheaf, spherical object, and spherical twist. So, and this is not the end of the story. So, questions. Are there other symplectomorphisms support linear Lagrangian submanifolds? And if yes, what can one say about the induced autoequivalence? And by the same construction, one can define a Dehn twist along a projective space. So here, I actually copy the previous table so the table is the same, but I just replace all the S and E with P, and they are the same. And then, so here P is a Lagrangian projective space, and you can define the Dehn twist near the Lagrangian neighborhood, and the curly P is a P object in the category. So it looks parallel. And the definition of P object and P twist are grammar mistake, are due to Hurstbus and Thomas, and motivated by the symplectomorphism, the twist along the Lagrangian projective space. And what is still unknown is whether the induced autoequivalence on the derived Fukaya category by the Dehn twist along a projective space is the TP. So let's go back. So in this picture with S and E, Sidel proved that the first column and the second column, they correspond to each other. And then, but for this one, actually it is easier to define the autoequivalence purely algebraically using P object. And then it is not known whether they are related. And so in my work with my collaborator Wu, so we prove that we give evidence that they are the same. So this is a Lagrangian, and you twist along the projective space, and it is quasi-isomorphic to, so cone is mapping cone in the triangulated A infinity category. And then the formula looks very similar to the projective twist defined purely algebraically. But we cannot actually determine the morphisms, so we cannot prove the theorem completely, cannot prove the results completely. But let me talk about something more interesting. So the question is whether spherical twist and P twist are related. They are of course related in some low-dimensional cases. So for Lagrangian S2 and Lagrangian S1, S and P are related. So the Dehn twist along a sphere twice is the same as the Dehn twist along the projective space. Okay. And what is more interesting to me is if we have a Lagrangian Rpn, Rp2n plus 1, then it is a P object in characteristic 2, but it is a spherical object in characteristic lot 2. Here I didn't define what is P object and spherical object precisely, but if you look at the cohomology, then I think you are convinced that this guy is a P object in characteristic 2 and not in characteristic lot 2. So the question is, what is the induced autoequivalence when the characteristic is not 2? Okay. And then there are some hints. So when the characteristic is not 2, then P is spherical, so you cannot define a projective twist. And it is and the induced autoequivalence is not a spherical twist, and it is also not a square of a spherical twist. So it seems that some mysterious guy. And
so we're talking about real projectives.
yeah, right, real. Sorry, real.
So, okay, do it again.
Yeah.
It's not. Okay, yes. Okay, fine. Yes.
Okay. Questions? So, and okay. And actually, it is a simultaneous spherical twist by two spherical objects. And so this example is interesting to me, and I want to understand more about the Dehn twist along length spaces or some other Lagrangians, and try to see. So you can see that the twist change going if you go to different characteristic, and I want to observe this kind of new whether this will give new kinds of phenomena of autoequivalence for bounded derived category.
What is simultaneous?
So because they are orthogonal, so twist and then twist.
Are the spherical objects represented by Lagrangians, or they're just spherical objects in the category?
You mean in the low dimensional case?
No.
Yeah.
It means, what are those two spherical objects?
Those two spherical objects. So
Geometric meaning.
so you can put different spin structure on it, or you can put different local
It's
system.
P with the two spin structures.
Okay.
And and right. So that's all for my talk, and thank you very much.
Some more questions?
Yeah.
Could you tell what P objects are in the half category of coherent field?
Yeah, it is